Hi class, welcome to exercise 10D, where we're going to introduce polynomials. Today, your examples and pre-learning will be example 8, evaluating polynomials. And your pre-learning for this example will be questions 1 and 2 in the new book and question 4 in the old book. And then we'll do example 9, which is deciding if an expression is a polynomial. And your pre-learning for this example is questions 4 in the new book and question 6 in the old book. Now this won't be the first time you've seen polynomials, you've actually used them before. However, they do have many names, so you might not have realised. Alright, we'll see you in the introduction. A polynomial, which contains the old Greek word for many and the Latin word for name, is a function where p of x is equal to an times x to the n plus a n minus 1 times x to the n minus 1, and continuing on until we get x to the 0. Each an is a real number and it's the coefficient of that x. And n is either 0, 1, 2 or 3 or any other non-negative integer. And when we're talking about a polynomial, n is the highest power of any x. And it's really the defining value of the polynomial. Because when we speak about a polynomial, we say that the degree of the polynomial is this n. So have you used these before? Well, yes you have. So firstly, we have a polynomial, p of x, which is just equal to 2. And that's a polynomial because I can rewrite that as 2 times x to the 0. So I'm sorry if that makes you groan. Now in this case, the real number coefficient is 2. And this polynomial is called a constant. And the highest power of x, you can see here, is 0, so it has a degree of 0. Then a p of x equal to 3x minus 2 is a polynomial, because that's equal to 3 times x to the 1 minus 2 times x to the 0, with real number coefficients of 3 and 2. And this, of course, is a linear polynomial function, which has a degree of 1. And of course, p of x equal to x squared minus 3x plus 1 can be rewritten as 1 times x squared minus 3 times x to the 1 plus 1 times x to the 0. And you can see the real number coefficients there. And of course, this is a quadratic polynomial that has a degree of 2. And a polynomial that has a leading term of x to the 3 is a cubic with a degree of 3. And we call a quartic a polynomial with a degree of 4. And quintic for a degree of 5. And as the polynomials get higher and higher degrees, there do exist names for them, but quite often we stop bothering to name them and just state their degree. And we could potentially have a degree of any size you want, okay? But my question to you regarding this next polynomial, is it a polynomial of degree 8? What about the x to the power of 7 or x to the power of 6? I mean, shouldn't a polynomial have everything? Well, actually, it is a polynomial. For this polynomial, you would say that a7, a6, a4, a3, a2 are all 0. So even though x to the power of 7, 6, 4, 3, and 2 exist, so to speak, in this polynomial, their coefficient is 0, so they end up adding nothing to the polynomial. And 0 is a real number. So to define it formally, we define the degree of a polynomial as the largest power of x with a non-zero constant. Alright, so do you think that 3 times the square root of x plus 2 is a polynomial? Or what about 2 times x minus 1 over x plus 2? I mean, we're just using x's here, right? Well, actually, both of these are not polynomials. Because I could rewrite the first one as 3 times x to the half plus 2 times x to the 0. We can see a power here that's not an integer. And for the second one, that's 2 times x to the 1 minus 1 times x to the minus 1 plus 2. And of course, the reason why this is not a polynomial is that we've got a negative power. Okay, so what about x to the power of 3 divided by 3 plus 2 times x squared minus 3 all divided by 5? Or x to the 4 minus 3 times x squared divided by pi times x. I mean, surely not. We've got this irrational number here. We're dividing by an x, so that's the negative power, I think. But let's have a look. So this one at the top here, I could rewrite that as just 1/3 times x to the 3 and 2 over 5 times x to the 2 and 3 over 5 times x to the 0. And that is a legitimate polynomial, so that's good. And for the next one, I can just follow through with the algebra here. We've got x to the 4 divided by pi times x. So that cancels out 1 power for the x. So we've got 1 on pi times x to the 3. And the other one, we can do the same thing, but we've got minus 3 on pi. And x squared divided by x is x to the 1. So that's minus 3 on pi times x to the 1. So here we've got x raised to integer powers that are positive or non-negative numbers. So that is legit. All right, let's write that down. All non-negative integer powers. And that's all it takes, okay? The other thing to take into account is the coefficients are real numbers, and 1 over pi and minus 3 over pi are real numbers. And by real numbers, I mean if you put it in the calculator, you'd get a number that fits on the number line. But having said that, it is pretty rare to see all these irrational numbers in there. We're not going to trouble you with those much in this unit. Now I'd like to pop over to GeoGebra using this applet just to have another look at polynomials. Okay, it's not going to be easy to prepare what I'm going to say here because I've created this applet with random numbers for the coefficients. However, it shouldn't matter too much because I just want to give you a broad description of what a polynomial is, and I've made sure that they're all integers and the first one's not going to be 0. Now, the degree of our polynomial is n, and I'm starting here with the constant function written in a polynomial form, x to the 0 times 2. So x to the 0 is always equal to 1, so we've got 2 times 1, therefore a constant function of 2. Okay, let's slide n, and here we go. We've got a linear function and a quadratic function, and you've seen both of these before. And you already know from the units that we've done this year that a quadratic means that we take x as our input and we multiply it by itself, and then multiply that by 5 in this case, and then we multiply x by 4, and finally we add 2 to it. Well, as we go to a cubic, it's just the same. Okay, we just insert an x value and we multiply it by itself 3 times and then multiply that by 5, so on and so forth. Now if I slide k here, we can see the output of this function for that x value. Okay, you can see the point moving around there, but also notice that p of k is equal to p of the number in there, and I've got the answer here. And if I pick on an easy number like 1, and 1 raised to any power is just 1, right? So we should have 5 minus 2 is 3 plus 1 plus 3 is 7. And sure enough, when x is 1, we got 7. And this is the same for a polynomial of any degree, including quartics or quintics. And as we slide n up to 30, you'll see that we get some weird and wonderful shapes. That's not a bad one. Wow, look at that one. So for this polynomial of degree 15, it's creating this weird shape here, but really, in the end, we're just taking any x value, multiplying it by itself 15 times, and then multiplying that by 3, and then we're adding it to the same value, the input value, multiplied by itself 14 times, and multiply that by 4, etc., etc. And you can see that it quickly goes right off to a big number very quickly. If I move k to 3, we've already got, was that 52 million? Wow. Now, as I said, we could go all the way up to 30 with this, And if you really wanted to, you could go a lot higher than that if you had the time and inclination. Now I just want to slide it back to cubics and quartics. So here's a cubic and here's a quartic. Now I just want to see if you can notice a fundamental rule of polynomials related to degree. So back to cubics and quartic. Did you notice it? Okay, what about linear and quadratic then? Let's go to linear, quadratic, linear, quadratic. Hopefully you did notice that if the degree is an even number, we have the same basic principle as this quadratic here. And that is that there's a middle bit and it goes positively on both sides of it. And it goes very quickly too. And if the degree is odd, like a linear function, then we head off to the negatives and then the positives. Now I'm not going to say why that's the case right now. I'll let you think about that. But I'm just going to say one more thing before we head back to OneNote, and that is that this is called the leading term. Okay, so if I change the n, the reason why it's called the leading term is because it very quickly takes over control of what's happening in our polynomial. But anyhow, let's go back to that OneNote. So apart from the weirdness and wonderfulness of functions and what they can look like, what I really want you to take away from that GeoGebra applet is to not forget that a polynomial is a function. And so what that means is p of minus 2 means that I'd place minus 2 where all the x's would be. The other thing is that the x with the highest power is called the leading term. And of course that's the power that has the degree. Alright, so I realize that some of this might be easy-ish to some of you, but there are some strange ideas and some definitions you do really need to get your head around. So I strongly recommend that you pause the video right now and do the building understanding questions in the new book, which translates to questions 1, 2, and 3 in the old book. And then when you come back, we'll get stuck into the next section. So as we stated in the introduction, a polynomial is just a function of x. So for polynomials such as an times x to the n plus an minus 1 times x to the n minus 1 and so on, then p of k is just equal to an times k to the n plus an1 times k to the n minus 1 for any k that's a real number. So of course we're allowing for k to be any number and we've subbed it in for x. But when you're evaluating like this, the smart move is to raise k to the powers first so that there's no confusion when k is a negative number. Anyhow, let's see this with some numbers in example 8, where for the polynomial x cubed minus 3x squared minus x plus 2, we're going to find the following. So first in part A, we're going to evaluate it for x equals 2. So as I was saying at the start of this section, we now put 2 in for x. Okay, so that means we're going to have 2 cubed minus 3 times 2 cubed minus 2 plus 2. So we've now got 8 minus 3 times 4 and a minus 2 and a plus 2. And in case you're confused, that's a 4 because I should have written 2 squared. Okay, the same as the 3 squared in the question. So 3 times 4 is 12 and minus 2 plus 2 is 0. So we're left with 8 minus 12, which is minus 4. Alright, and we're going to continue working with the same polynomial when we find its value when x is equal to minus 3. So as our x is equal to minus 3, I'm going to now sub minus 3 in for x. And straight away with the minus signs, you can see why it's really important to use the brackets. Okay, so minus 3 cubed is minus 27, and minus 3 times 9, and minus a minus makes plus 3, plus 2. So minus 3 times 9 is minus 27, and 3 plus 2 is 5, so we've now got minus 27 plus 5, and 27 times 2 is 54, so we've got minus 54 plus 5, which is minus 49. And we're done. So that's how easy it is to evaluate a polynomial. You just sub in the value we're asking for in the place of x throughout the polynomial. Alrighty, you should pause that video now and do questions 1 and 2 in the new book or question 4 in the old book. And then when you come back, we'll see you in the next section. When deciding if an expression is a polynomial, we need to understand that a polynomial is defined as some number an times x to the n plus another number we'll call a n minus 1 times x to the minus 1, and then you keep on going, adding different coefficients of x to the each power all the way down to 0. And the key to this is that all these coefficients, all these a's, are real numbers, and all the powers are non-negative integers. So non-negative means 0 or greater, and integers, of course, just mean whole numbers. Though it's probably very clear since the last section, but it's really important that you understand that x is the same variable. Alright, let's move on to example 9, where we're going to decide if the following expressions are polynomials. Alright, in part A, we've got 4x squared minus 1 plus 7 times x to the 4. So obviously 2 is a positive whole number, and 4 is a positive whole number. And on top of that, minus 1 is the same as saying minus 1 times x to the 0. So when you take that into account, that means all the powers of x are 0 or greater integer values. So yes, it's a polynomial. Alright, let's move on to part B, where we've got 2x squared minus the square root of x plus 2 on x. So x squared is the same as saying x to the half, and 2 on x is the same as saying 2 times x to the minus 1. So a half is not a whole number, and minus 1's a negative number, so that means that both of these terms violate conditions of polynomials. So therefore, it's definitely not a polynomial. Alright, I don't know if I really need to wish you the luck that I like to sometimes, because it looks pretty straightforward to me, but you should pause the video now and do question 4 in the new book or question 6 in the old book to check that you have got it. And then when you come back, we'll be able to summarize this lesson. So there's a reason why I did jump from chapter 7 to chapter 10, and that's because we covered functions first, because I really want you to think about polynomials as functions. And you saw how easy that made it when we just subbed in an x value with the brackets like that. Now, this is an easy introduction, but really take some time to absorb the definitions here, because in the next few lessons, we're going to be multiplying, dividing, and graphing them. And I don't know if it looks like it to you right now, but trust me, polynomials are amazing. If you indulge me for 2 minutes here, I'm going to show you that in a few years from now, you'll be able to do things like I'm about to demonstrate to you on this GeoGebra applet. And that is graphing any function you can think of using polynomials. I mean, how do you think a computer can graph such complex functions? Let's consider a function we looked at in our previous unit, and that was 2 to the x. Do you really think a computer could work out 2 to the half or negative a half? I mean, they're square roots. Of course, it's going to take too long for it to find all of those, not to mention the cube roots, etc, etc. But what a computer can do is multiply values together using whole number powers. So you can see 2 to the x here on the screen, and the name of the function we're looking at is here as well. And you can see this polynomial here, and that's making a linear function, which you can see as a blue line. You might notice that it actually approximates the graph around about 0 perfectly there. Well, let me turn that line into a quadratic. Seems to get a bit closer. Let's try a cubic. Closer. Quartic. Closer again. Hopefully you're noticing the coefficients here. It makes life a lot easier if that a is at 0. Now you'll see that we've got x squared and x cubed and x to the 4 with these crazy coefficients. Now if I keep on going, I can make n go all the way to 30. Do you notice how close it's getting to the line? So if I kept on adding more and more coefficients, it would actually end up making the line exactly the same. And like all my applets, you're welcome to play with it with the link from the OneNote. But let's have a look at one other function before we head off. Sine of x. And we're going to be looking at this later on this year. So let's have a look at n equals 1. We have a linear y equals x. Let's have a look at a quadratic and a cubic and all the way up to the power of 5. And you can see it's already starting to kiss the line for quite a bit there. And if I keep on adding more and more terms, we're getting closer and closer to sine of x. In fact, let's go all the way to n equals 30. So wow, isn't that amazing? Hopefully this will inspire you to keep working hard through a unit that probably starts off feeling a little bit too easy, but all of a sudden might feel a little bit too hard. Alrighty then, a successful student will, once completing the lesson, know the general form of a polynomial, know the meaning of the degree of a polynomial, and the names of common polynomials. And finally, be able to use function notation for a polynomial. Alright, well done. We'll see you in the next lesson, whether that's in class or in the next video. Bye.